Welcome to one of MidAmerican Energy's combustion turbine power plants. In this plant, combustion turbines convert fuel to mechanical energy to generate electricity. Combustion turbines can be powered by natural gas or fuel oil. Oil and gas were formed when animals and plants died and sank to the bottom of ancient seas and lagoons, where microscopic bacteria caused the decay of the animal and plant material. Layers of sediment covered them, and as the number of layers increased, so did the pressure and the temperature. This turned the rotting material into hydrocarbons that make up oil and gas. The hydrocarbons mixed with water and sand and gradually seeped through the porous layers of rock along with bubbles of gas. Eventually, the oil and gas would encounter a layer of rock that it could not pass through. It became trapped like water in a sponge, forming oil and gas deposits. Once natural gas or oil deposits are located, these fuels are taken out of the earth and refined before they are used to generate electricity. Oil and gas are removed from the earth through wells that are drilled down into the deposit. If a well passes through porous rock containing oil and natural gas, internal pressure may force the raw fuels to the surface. However, this pressure usually subsides, and the fuels must eventually be pumped to the surface. When the natural gas and oil have been removed from the ground, they're transported to a treatment plant. At the plant, they go through a process that prepares them to be used as fuels. After treatment, the fuel can be sent to a power plant. This facility is called a combined cycle power plant. In the first cycle, a combustion turbine burns fuel to power an electrical generator. In addition to generating electricity, the combustion process also results in a constant flow of hot, high-pressure exhaust gas. In the second cycle, the hot exhaust gases pass through a heat recovery steam generator, where the hot gases convert water into high-pressure steam. The steam is routed to a steam-powered turbine, which powers another electrical generator. By recycling the exhaust, additional electricity is generated without the need for additional fuel. Generating electricity with a combustion turbine begins when filtered outside air is pulled into a compressor. The air is forced through the compression chamber by a series of rotating and stationary blades. As the air travels through the compressor, its pressure and temperature increase as it's forced into a smaller and smaller space. This increase in pressure forces the air through the rest of the combustion turbine. The high-pressure air from the compressor is directed to fuel injectors that release fuel into the air. The fuel and air mixture flows into combustion cans located around the turbine. Within the cans, a flame ignites the mixture, resulting in hot gases that expand into the turbine area. The hot, high-pressure gases then blast through the turbine, spinning a series of turbine blades connected to a long shaft. As the shaft turns, it provides mechanical energy to turn the blades of the compressor, and also rotates an electromagnet within the electrical generator. The rotating electromagnet within the generator creates an electrical charge. The electrical charge creates an electrical current that travels through tubular aluminum conductors to a step-up transformer outside the plant, where its voltage is increased. The electricity is then sent to the power lines that carry it to homes and businesses. After the hot gases turn the combustion turbine blades, the gases exit from the turbine as exhaust. However, the gases are still hot, and the heat can be recycled through a heat recovery steam generator. The heat recovery steam generator turns water into high-pressure steam. The steam is used to power a steam turbine that generates additional electricity. In the heat recovery steam generator, the hot gases pass over tubes that have water running through them. The hot gases boil the water in the tubes, turning the water into steam. As the water turns to steam, its pressure increases. This high-pressure steam is piped to a steam-powered turbine. As the steam rushes through the turbine, It turns blades attached to a long shaft. The other end of the shaft is connected to an electrical generator. As the turbine turns the shaft, it causes large electromagnets to rotate within the generator, creating an electrical current that is sent to a step-up transformer. After the steam turns the turbine blades, it leaves the steam turbine and passes through a condenser. The steam is turned back into water as it is cooled by a separate water supply, known as circulating water, flowing through the condenser tubes. The condensed steam is then returned to the heat recovery steam generator, where it is again turned into high-pressure steam. The circulating water is piped to a cooling tower to lower its temperature, and is then returned to the condenser to be used again. The hot gases that pass through the combustion turbine contain emissions of carbon monoxide and nitrogen oxide that need to be removed before the gases are returned to the atmosphere. To accomplish this, the gases first pass through an oxidation catalyst unit within the heat recovery steam generator. This unit has many small plates in it, like a radiator. The plates are coated with a chemical known as a catalyst, which interacts with the carbon monoxide. As the gases pass through the unit, the catalyst converts the carbon monoxide into carbon dioxide, reducing it by approximately 80%. Nitrogen oxide emissions are controlled before leaving the heat recovery steam generator as well. As the first step in this process, the gases are injected with ammonia. They then pass through the selective catalytic reduction unit, which also contains many small plates coated with a catalyst. As the hot gases pass over the plates, the nitrogen oxide reacts with the catalyst and ammonia and turns into nitrogen and water. The selective catalytic reduction unit reduces nitrogen oxide emissions by as much as 90%.